Well, let's get started. I'd like to call on Ian Axford to give an introductory talk on the interrelated nature of magnetospheric-ionospheric coupling processes.
Well, it seemed a terrible time to have a meeting at 8 o'clock in the morning just after a breakfast, which I didn't taste. I have a great problem in giving this talk because I don't quite know what the subject is about. The reason being that, being older than a lot of you now, I suppose, I was there when the term magnetosphere was invented. And the magnetosphere at that time, and I hope now, means the region between about 120 kilometers and everywhere else in the Earth's magnetic field. So it's a little difficult to talk about Magnetosphere-Ionosphere coupling, since the ionosphere is in fact part of the magnetosphere. Could I have the first slide, please? Just to remind you of this, people tend to take definitions for granted. And I think the magnetosphere, the definition of the magnetosphere has just either been forgotten or some energetic international committee has redefined it without making any sense. This is what happens. What I did just to make this point was to dig out a few ancient papers just at random, which was sufficiently ancient that the author felt that he had to define or remind his reader what the magnetosphere was in the first place. I don't know if you can all read that, but the first I just clipped out of a review paper by Colin Hines, and he just points out that the magnetosphere is defined by its dynamical behavior. It's that part of the Earth's environment in which the motion of ionization is dominated by the magnetic field. That's the most important thing of all. You can see then why it's the region from the ionosphere upwards, of course, because the motion of plasma in the ionosphere is dominated by the Earth's magnetic field, at least above altitudes where the gyro frequency is comparable to the collision frequency. Now, at times, one likes to, in fact, push this even down further and take it down to the place where the electron gyro frequency is comparable to the electron collision frequency, which brings the thing down to maybe 90 kilometers. The next definition, or the next comment, the one in the middle, came from who? Somebody else. Well, it doesn't really matter. It says the same thing anyway, that it's from about 130 kilometers upwards here, because at that time it was thought that was where the ion gyro frequency and collision frequency were the same. In fact, we now know it's more about 120 kilometers. And the last comment is from a review paper by Kern, again saying the same thing. The region extends from the E region of the ionosphere upwards to the outer boundary of the geomagnetic field. Have the next slide, please. Oh. Thanks.
Good.
Okay.
It worked.
Well, from what I said then, you can see that basically the ionosphere is the place where convection occurs. It's not surprising because the magnetosphere is the place where convection occurs. It's not surprising because the first ideas about the magnetosphere were ideas about convection. Essentially, the definition that I gave you amounts to the following, that the magnetosphere is the place where E plus V cross B is a good approximation for Ohm's law, at least in general. That is, the mean motion of plasma, at least of the lower energy plasma, is essentially E over B. And this equation, as it stands, if you take it with Faraday's law, yields the familiar hydromagnetic frozen field theorem. And so one can, in fact, make good use of the frozen field theorem throughout the magnetosphere until you get down to at least altitudes of 120 kilometers and less. Of course, one must be very careful and understand what the theorem means and when one should patch it up. In this Ohm's law, if you just take it in its traditional form, the sort of form that you see in Spitzer's book, for example, you'll notice that there are a number of terms out of here. Whoops, what happened? I'm talking about some other slide, I'm afraid. Did that my good slide come on?
Yeah, well, this wasn't your next one, right?
No.
This isn't the next one.
Looks like it's skipped to the turn.
I think I know what's happened. Yeah. Okay, it doesn't matter. Go back to that one, Andy. I realize what's happened. It's my fault, sir. I changed the order of my pages without changing the order of the slides. So we'll have a slide. As I said, it's far too early in the morning to be giving a talk like this. So, right, well, I thought then I ought to say what magnetosphere-ionospheric coupling might be, if there was any necessity for saying so. If we divide the magnetosphere into the ionosphere and the rest of the magnetosphere, then we more or less have it right. And then the coupling can be thought of in a simple-minded way, at least very simply. The coupling can consist of exchanging momentum, exchanging energy between the various regions. And in the process of doing this, you might think about the exchange of stresses hydromagnetically, or if you want to think of it another way, the exchange of current and electric field. Now, first of all, a mass exchange, if we consider the various possibilities that we have, from the ionosphere upwards, so the first line there reads up, the exchange of mass, which is important, is essentially the polar wind, if you like, or the processes which cause the ionosphere to flow upwards and in some parts escape from the Earth altogether, or in other parts of the magnetosphere replenish or build up the plasmasphere. Just from looking at the way the plasmasphere sits in the middle of the magnetosphere, it seems pretty clear that beyond the average position of the plasmasphere, which is latitudes of 60 to 65 degrees, essentially anything that flows upwards is lost by one way or another. It may not flow out along open field lines immediately, but it gets lost pretty soon afterwards. Presumably this is important for a number of reasons, but especially for the Earth's helium budget, it seems that you lose enough helium this way to be more or less make it possible to account for the balance of entry of helium into the atmosphere from below, from the Earth, and loss. There may be other loss processes, of course. Now, coming the other way, mass going down from the magnetosphere into the ionosphere, or the outer magnetosphere into the ionosphere, there are two main things that matter. The most mass comes down in the form of plasma, low-energy plasma from the plasmasphere, which somehow must contribute to the replenishment of the night-side ionosphere. There has to be a decent sort of balance between the plasmasphere and the ionosphere, and one must expect that at times the plasma moves downwards, not just always upwards. As far as energetic particles are concerned, the total mass involved is pretty trivial, although for some species of energetic particles coming in from the outside, the replenishment or the contribution that you get to the atmosphere may be significant. And I think that this is particularly true for helium-3. That isn't supposed to be helium or H sub e, it's supposed to be He super 3. That seems to be at least one of the major sources of the atmospheric helium-3 that we have, although there is at least one other that's important. Well, that's a simple-minded way of looking at mass exchange between the ionosphere and the outer magnetosphere. What are the questions that we would ask? Well, I've written them down here. The first one, which I think is one of the most interesting ones that faces us at the present time, is that there's good evidence now from the measurements of the Lockheed group that there are energetic singly ionized oxygen and helium ions in the magnetosphere, ions with energies of a few kilovolts. And it seems quite impossible to get these from any other source but the ionosphere. For instance, solar wind oxygen ions have all the wrong characteristics. To begin with, they're charged maybe 6 or 7 times. It's very difficult to get them all neatly down to be charged only once without doing worse damage. And furthermore, the energies are all wrong. The energies of a few kilovolts are just wrong for solar wind oxygen ions, which begin with energies of several kilovolts when they're outside the magnetosphere. If you bring them into the position where these ions are observed, they must inevitably be accelerated no matter what happens to them. So they ought to have energies of some tens of kilovolts at the positions where they're observed. And that's not the case. So I think it's pretty clear that these are ionospheric ions which have been accelerated to modest but significant energies. And we need to understand what happened there, especially as the fluxes seem to be extremely large, in fact, comparable with the proton fluxes at times. The second question was what happens to pieces of the plasmasphere which get torn off? I said detached regions of the plasmasphere here. There is, of course, a question as to whether you actually detach anything or you just pull off streaks and leave a long connecting ribbon. That's something we need to understand, I think. The third question I've put down here is about how do outer magnetospheric features relate to ionospheric features. It's a rather complicated one. In the outer magnetosphere, we have everything nicely controlled by the Earth's magnetic field, but unfortunately it's rather difficult to understand just what the shape of the Earth's magnetic field really is. I think Don Fairfield has wrestled with this problem more than anyone, but one always knows that if you're out in the magnetosphere looking at the results, observations of one particular satellite, one can never be very, very confident about where the field line at your satellite happens to hit the Earth, or even where the field line goes when it's in the opposite direction. There are endless arguments about how far field lines are extended into the tail and where field lines in the vicinity of the polar cusp go. Do they straggle back into the tail or do they close on the Earth comparatively closely? So we have a great difficulty then in trying to understand how features in the magnetosphere, that is the boundaries, for example, of regions containing energetic plasma and so on, how those relate into ionospheric features, auroral arcs being a particular example of that. Finally, I've got this question about how easy is it for plasma, this polar wind type plasma, to escape along open field lines. The problem there is that the plasma doesn't move all that fast, a few kilometers per second maybe 10 kilometers per second, and the field lines don't stay open for long. Can they get out? Can the plasma get out before the field lines close again? That I don't really understand at this stage. Now, the next line of attack to this general scheme of things is to consider momentum exchange between the ionosphere and the magnetosphere, the outer magnetosphere. This basically is like this. If you can consider momentum exchange from below, the important thing to notice is that if you move the neutral atmosphere around at ionospheric levels, you inevitably start moving the plasma around. And the magnetosphere being what it is, this means that the rest of the magnetosphere starts moving accordingly. The most important atmospheric motion which causes the magnetosphere to move around is the rotation of the atmosphere, of course. There's no way of stopping the magnetosphere responding accordingly, that is rotating in some sense, once the atmosphere is rotating, simply because there's no counteracting torque to prevent the magnetosphere moving as well. At least in general, that's not the case. There is the possibility that the solar wind can apply significant torques, but it is rather difficult to understand them, as I will mention again in a minute when we come to the questions. Now, the other way in which the atmosphere can move the magnetosphere around is, of course, in tidal motions, or even in smaller scale wind motions. Unfortunately, as far as the more exotic or interesting features of the magnetosphere are concerned, the tidal motions are just not really very significant, because their effects are mostly noticeable near the equator, where the tidally induced velocities are comparable with the Earth's rotational velocity. And there they can, for example, distort at least the ionosphere and make the so-called equatorial anomaly. But I don't really believe that the tidal effects have any first-order effect on, for example, energetic particles in the magnetosphere. The reason being is that the tides produce, if you like, an electric field pattern or potential pattern, which is more or less stationary in a frame viewed from outside the Earth. And by the time you combine the electric field due to rotation with the tidally induced electric field, you find that rotation just overwhelms the other, except right at the equator. Now, momentum exchange downwards is much more interesting. This is in contrast to the mass exchange. Magnetospheric motions, that is magnetospheric convection, can start the upper atmosphere moving. And in the F region, it does this very quickly. It's just a matter of tens of minutes before the atmosphere must start to follow the motion of any plasma. Roughly, what matters is the neutral ion collision time, which is not the same as the ion-neutral collision time, of course. There has to be a factor of the density ratio involved. But of course, since the density in the F region the neutral density in the F region is not very large, one has not an unfavorable ratio to compete with. At the E region, it takes several hours, but it's perfectly possible that rapid motions could be induced there, especially when the E region is, say, unusually dense as far as the plasma is concerned. And I believe that there are now lots of good observations which indicate that this is certainly the case. Presumably also, sudden changes in the state of magnetospheric motions can produce sudden changes in the atmosphere, and we all have heard about the observations of Chuck Wilson on infrasonic waves and older observations on traveling ionospheric disturbances produced by large or sudden large changes in the state of motion or convection at auroral latitudes. So our questions as far as momentum exchange seem to be just two really important ones. The first one on the momentum exchange upwards is how does the tail of the magnetosphere cope with the desire that the ionosphere wants to make it rotate? Say that again. The ionosphere at the foot of the tail, that is in the polar cap, is certainly rotating with the Earth, and the neutral atmosphere there is rotating with the Earth to a first approximation. The tail of the magnetosphere would want to do likewise. However, the tail of the magnetosphere is also connected on open field lines to the solar wind, and it doesn't want to rotate. So there's a sort of a problem which the ionosphere and the solar wind have to sort out. The ionosphere would probably like to win, since there's a tremendous amount of inertia involved there, and there's not much in the solar wind. But just how it does it, if it does it, isn't by no means clear to me. I don't think anyone has quite understood what to do with this particular problem. The second question is one which has, I think, become more important in recent times with the Chapman observations of large neutral atmosphere winds at ionospheric levels produced apparently by external convection. Is how these winds, once they're started, affect the rest of the magnetosphere. If you start the neutral atmosphere moving, you've got to stop it again somehow or other, and in the process of stopping, that will start the magnetosphere moving again. So there's a complicated interaction there which is worth looking into very carefully. Now the final way of going through the interaction or coupling in these lines is to look at energy exchange, and here I think it's pretty trivial in some ways. Upwards, the energy that can go upwards is almost entirely photoelectrons if you're interested in real energy. And here one presumes then that the temperature of the plasmasphere and the speed of the polar wind, that is the speed of escaping plasma, ought to be strongly influenced by photoelectrons. The other things, whistlers and hydromagnetic waves, accelerating particles, is something that people have talked about for years and years and years, but I don't think anyone has ever demonstrated or taken seriously the possibility that this is a major contribution to the energetics of the outer magnetosphere. This last comment about convection induced by rotation and tidal motion having negligible effects is certainly true for the Earth. The fact that the Earth rotates doesn't really make radiation belts for you. So in the case of Jupiter, this is another matter, because there the rotation speeds are going to be many hundreds of kilometers per second, and if one just spins up any cold plasma that's sitting there, one has already kilovolt plasma. and one could perhaps start to use that for more interesting things. Energy exchange downwards, again, is very, very important. It takes place in all sorts of ways, but if you think of it in terms of transport coefficients, there's Joule heating in the ionosphere, which we see very clearly in the auroral zone, viscous heating, which is just about as important, although one tends to forget it. Thermal conduction, well, that's just a way of looking at the way energetic particles come downwards. If you think at least of the low energy, but more moderately energetic magnetospheric plasma, the electrons, on finding their way down into the cold ionosphere, will in fact be doing what one can consider as thermal conduction. As far as energetic particles are concerned, it would be an unreasonable extension of the idea of thermal conduction to call aurora just that. But nevertheless, energetic particle heating in the auroral zone, at least, produces very substantial ionospheric heating. Perhaps it can even make the top of the atmosphere explode upwards at times. That's important because it appears from observations of satellite drag that there is a substantial non-solar contribution to the heat budget of the upper atmosphere, and presumably it comes in this way from all of these various sources. Again, as far as atmospheric budgets of minor species are concerned, the temperature of the upper atmosphere can be very important, and presumably can be controlled to a large extent by heat sources of this type. So we're thinking here mostly of the loss of hydrogen from the Earth. Now, if one wants to think about other modes of transport or think about the actual mode of transport of momentum and so on between the outer magnetosphere and the ionosphere, the best way, as far as I can see, is to think of stresses. Now, I'm going to talk later in terms of currents and electric fields, but that is not a very convenient way to do it always. One can't understand the whole problem of coupling, I think, unless one thinks of forces or stresses in the first place, because the magnetosphere is a very complicated place, and it's almost a waste of time unless you think of the problem in some self-consistent way. By that I mean that the current, for example, in the magnetosphere is not just a current which God gives you. Somehow or other the current has to fit itself in nicely with B, because there's a nice equation relating them, J equals QL B. And you can't just say that the field is there, let a current flow. It isn't like that. The way the magnetosphere is built is that all the currents close within the magnetosphere. It's not like a laboratory plasma where you might be able to close some currents in some external circuitry, and you have external pieces of concrete and pieces of steel and pieces of glass which take up stresses for you. In the magnetosphere, all the stresses exerted by the plasma and by the magnetic field must be in balance between each other. You can't have anything externally holding on to things for you. There is one counter example, that is the Earth itself, of course, which does stop the magnetosphere from blowing away, but we won't get too hung up on that. Well, the main components of any stress balance between the outer magnetosphere and the ionosphere are these, which I've listed here, 5 of them, the last one being not very important. The first one is the inertia of the plasma. Now, in the Earth's magnetosphere, this is not too important, mostly, except in the plasma sheet, where we know that there are velocities, streaming velocities of the plasma of several hundred kilometers per second. Clearly, then, the inertia of that plasma must be very important indeed in that region. In the case of Jupiter, though, the inertial effects associated with rotation are obviously important. So that term does play a very large role in stress balance in Jupiter's magnetosphere. The next component is the pressure gradient. Well, obviously that's just the ring current. In part, the pressure of the ring current causes the magnetosphere to swell a little. However, the most important part of the magnetosphere where pressure gradients matter is in the tail, notably in the plasma sheet, where the extension of the plasma sheet is essentially represents a balance between items 2 and 3 on this in this equation, set of this equation. The third component, that is the Maxwell stresses, J cross B, is obviously important everywhere, since that's what the magnetosphere is made of. But In general, and throughout most of the magnetosphere, the Maxwell stresses, that is item number 3, are in equilibrium with themselves. That is, the curvature stresses and the gradients of magnetic pressure just balance each other nicely. However, there are several regions where the other components of the equation have to balance the Maxwell stresses. These are notably in at the magnetopores, of course, in the tail, where the pressure gradients are very important, in the ionosphere, where the reaction with the neutral atmosphere is important, and that's about it. The fourth item I've called sliding friction. I put in the word sliding because the friction doesn't start to work until the plasma moves. This is important in the ionosphere. It represents just a friction between plasma and neutral atmosphere, essentially. The last component, gravity, is almost everywhere unimportant, except as far as low-energy plasma is concerned, namely in the upper ionosphere and the plasmasphere. Okay, but I said I would talk about this in terms of currents. So let's try to see what sort of currents are flowing around the magnetosphere. And let's try to dissect the magnetosphere in, first of all, well, not dissect, but build it up to the most simple form. And consider first a hypothetical magnetosphere where there are no shear stresses or transverse stresses at the magnetopores and no plasma sheet. No ring current, if you like, but that's not so important. Now, in this case, you have a Chapman-Ferrari type magnetosphere. I've sketched a view of what it might look like from the sun. It's the traditional Chapman-Ferrari magnetosphere on the top, and the bottom, what such a magnetosphere might look like in reality. And the hard lines are field lines, and the dashed lines are current lines. You can see then that the current closes around the surface of the magnetosphere, coming out of the blackboard, out of the slide here, and going in here where there's a cross. If you look at it from the front, it's the same sort of thing. Current goes this way, around the two neutral points. In this case, the neutral points are neutral points, and the cusp in such a magnetosphere would be just a sort of a field line or a funnel around the field line. The next slide shows what might happen if you add some shear stresses at the surface of the magnetosphere, viscous stresses if you like, but no plasma sheet. All this does is pull the field lines away from the sun a little bit, and as far as the currents are concerned, what it does is add currents which flow into and out of the surface of the magnetosphere. They don't close through the magnetosphere so easily though. They have to close down field lines across the ionosphere and back out again. As a consequence of this, the field lines in the ionosphere are bent back away from the sun so that the Maxwell stresses in the ionosphere can take up the extra stress forced on the magnetosphere by the solar wind. If that doesn't happen, then the Earth has to take up the stress, and of course it does do that. There are Earth currents always involved with these things. So the Earth does indeed take up part of the stresses. In this case, the dayside neutral points are no longer neutral points, but they'll become lines. They'll become something much more like one type of polar cusp. The type of polar cusp which I don't like is the sort that doesn't have interplanetary magnetic field lines in it. But it would be a line sitting around the dayside of the Earth. Now, if one goes a little further, well, not a little further, but if you take away the surface stresses, the transverse surface stresses, just leave normal stresses, but add in a plasma sheet, then you get very much the same sort of extra currents. But this time the current, instead of just going into the surface and closing down the field lines, will have to go right across the tail. And it will come out this way and close over the surface of the magnetosphere as these dotted lines show. But also it will close in part through the ionosphere, depending on the distribution of plasma. That's a very complicated problem. Now, if one gets towards a real magnetosphere, where reconnection between the interplanetary and magnetic fields, geomagnetic fields, is important, one has a very complicated problem. Here I've just tried to show, using an old picture produced by Levy, Petchuk and Cisco 10 years ago, where the relevant currents go. They're really very complicated. There's a shock wave to begin with, and the shock wave, if the field outside is southwards, which is the interesting direction, has in it currents which go into the paper. Around the surface of the magnetosphere, there are a whole lot of currents which come out. Now, whether these link or not is not too clear to me. I don't see why they shouldn't. But anyway, again, there will be currents which go down field lines into the magnetosphere, into the ionosphere, closing across the ionosphere and coming out again. I try to indicate that here. This is supposed to be a slice looking from the sunwards direction at the same picture. There will be currents going across the shock wave, going down the last field lines and perhaps in between as well. Some crossing, some coming back across here, and some going down into the ionosphere, across, out, up, like that. So, again, in this case, the field lines in the polar cap, at ionospheric levels, have to be pulled back away from the sun, again, to take up the stresses. But it'll only be the open field lines in here, which are pulled in this way. And so you must expect, naturally, that the polar field lines come back, whereas the field lines in this donut at lower latitudes more or less stay the way they want to be. You must expect then that there's a shear in the field here, so that the fields do this. And that's been observed, and it's not surprising. However, what does all this mean? What we notice is that if you think about the magnetosphere in this way, is that this sort of discussion that I've given you, which is a hydromagnetic discussion, has led automatically to current sheets which are very thin. You can't avoid it, in fact. A hydromagnetic treatment will always do that for you. This is the slide that I'd lost a long time ago. Let me just explain what was on it. We have an Ohm's Law. We say that the magnetosphere is the place where that is a good approximation for the motion of at least the low energy plasma. If you take that equation together with Faraday's law, you get the frozen field theorem, which I'm fond of using in this situation. And the equation is good for protons or ions down to 120 kilometers and for electrons down to less than 100 kilometers. There are various things missing in an equation like this, and it doesn't matter how you invent the equation, there will always be things missing. But they look like this. A thing here which really represents a Hall effect, the effect of electron pressure gradients, the effect of electron inertia, the effect of collisions either with background neutrals or between the particles themselves or between particles and waves, it doesn't matter. Plus anything else you like to invent. Now, the problem that we have to consider in considering ionospheric convection is whether any of these really matter. And they certainly do in some places. They will always matter in some times and at some places. One has to hope, though, that places where they do matter, or the times that they do matter, are short or localized. However, this can't always be the case. And just as a final demonstration of this, one which you're familiar with, if you consider the boundary between open and closed field lines in the polar cap, and here I've sketched the afternoon side boundary, the situation looks like this. The magnetic field lines come downwards in the north polar cap. There's an electric field this way, towards an infinitely thin current sheet, infinitely thin in the hydromagnetic sense. The current goes up the field lines in this case, across coming from the ionosphere on either side. The convection velocity is out of the paper on one side, into the paper on the other, and the magnetic field lines are bent this way and that way, so that the field shears as you go through. The potential distribution across a line like that is like that, and the field and the normal field and the velocity have a step. Now, on such a line, since the total current is finite, J, the current intensity, becomes infinite. And clearly you have to do something about that, because all the things you've ignored in Ohm's law suddenly start to become important on such a system. Now, here I've drawn this as in the way it might happen in a perfect magnetosphere without anything fancy happening. Here, all the electric potentials close in the D region of the ionosphere and below, simply because it's very hard in the usual situation to maintain large potential gradients in the ionosphere and above it. However, this isn't necessarily true. that the electric field parallel to the field lines exists only in the D region, because the plasma can always invent other ways to allow the electric field to soak upwards. And on this last slide, second to last slide, I've shown what happens in that case, and I presume that there'll be a good deal of discussion about this at this meeting. One would expect that if the current is somehow limited, that is the J, not the total I, the J is somehow limited to some level beyond which you're not allowed to make it go, then somehow the electric field has to have a parallel component somewhere. And I've sketched it, what it might look like if it was up here. Here, the current, instead of being a delta function, is spread up to some limiting value. That makes the whole boundary smear out so that the velocity shear becomes finite, the field turns over in a gradual way, and the potential at some level at least doesn't have sharp corners. There is a big question though that we have to consider, is just how and where does this potential drop occur? There's good evidence that it does occur in terms of the spectra distribution functions of auroral particles. But it is important, I think, to just discover whether it occurs in a sheet, which Lars Bloch will talk about, namely an electrostatic double layer, or whether it occurs in a sort of a distributed way, just as a consequence of some instability which produces an effectively small conductivity. Well, let's look at the last slide and summarize what we found out from all of this. What did you learn from what I was saying, if you are still awake, or have not yet? If you've awoken, I mean. First of all, that the currents, electric currents, are very complex and difficult to sort out. In fact, you have to know everything before you know what they are. It's in fact impossible to start from the currents and decide what the magnetosphere is doing. You have to, the way I argued, and the way everyone must argue, is that you don't know the currents until you know the magnetic field. And of course, if you know the magnetic field, you know everything anyway. But nevertheless, it's important to look at the currents because of these infinities, these high-intensity currents which must inevitably arise. The second comment I made on the way through, that there is an important distinction between laboratory and natural plasmas, namely that the magnetosphere and anything else that's natural has to be entirely self-consistent and entirely self-contained. The currents have to close within the plasma. They can't close through any external circuitry which you have at your control. The third point is that you inevitably expect sharp boundaries between regions of magnetic field which have different characteristics, namely between the open and closed regions of the magnetosphere, but also wherever there's some sharp feature in the magnetosphere itself, a boundary between hot plasma and cold plasma, for example. Anything like that will cause parallel currents, if you want to put it that way. And these must automatically arise. Finally, when you have such parallel currents, the first-order hydromagnetic treatment will always make the current intensity infinite, despite the total current being finite. And clearly, you have to look to see whether that's a reasonable possibility, which it's not. So our questions then are, as to what extent is the parallel current limited? How big can it be? And how wide then does the current, how broadly does the current have to spread out to prevent too large currents flowing? And then, in line with this, does the limitation of the parallel current result from a long, thick region with lots of wave-particle interactions, which give you an effectively large resistivity, or does it result from a double layer, which is certainly a possibility, and certainly these things exist, or is it a combination of both? Who knows? So I'll leave it to you to understand, to work these things out. Having made my plea that the magnetosphere is in fact got the ionosphere in it as well, and having made a long talk which contradicts what I've been saying, as far as coupling is concerned, perhaps I ought to stop. Thank you. What do we do now?
Other questions? Let's get it.
That second slide from the end, was that supposed to represent a charge sheet
Of course.
in a Royal Arc, for example? Or,
of course. If there's a discontinuity in the normal component of B, it's inevitable that there's charge there. But you never measure the charge, so why worry?
Yeah, okay.
That's another point I wanted to make. Currents. It's very difficult to measure currents as well. You measure B and you infer the currents. So, but charge is far worse. So it doesn't help to know that it's a charge sheet, as far as I can see. Except perhaps in keeping track of the directions of currents. I have difficulty with that.
I'm not too clear, maybe, on what the Chapman-Ferraro problem is. To me, it has always been a boundary condition. So that assuming that something is a Chapman-Ferraro solution doesn't exclude interior currents.
No.
So that, for instance, if you switch a magnetosphere on that's not in equilibrium, there will be interior currents.
No, I just used the word Chapman-Ferraro then in the historical sense. That was what their magnetosphere looked like, which had no interior currents. Yeah, that's right.
One of the questions that you raised is how the polar magnetosphere could cope with the requirement that the ionosphere has to co-rotate with the Earth while the tail has to stay fixed. Isn't that related to the problem of field lines disconnecting and remerging, and that some of the field lines now co-rotate and others don't?
It's certainly all mixed up with the question of field line reconnection. Field lines which are closed within the magnetosphere have no difficulty in rotating with the magnetosphere because there's very little torque that you can exert on such field lines to prevent it. In the case of Jupiter, this is not true because the inertia of the plasma requires considerable torque to get the plasma to rotate in the first place. As the plasma changes its radial position, then you can expect a lot of non- or partial co-rotation, temporarily at least. The problem in the polar ionosphere is that you keep changing field lines from a closed to an open configuration. Once they're open, then the rotation has to start the solar wind moving, if you like to think of it that way. They're not prevented from rotating by any means. There's a tussle between the solar wind and the ionosphere. And it's rather difficult to see who wins that tussle, or if there's any victor, whether in fact there's just a disequilibrium of some sort.
You started the latter part of your discussion by noting that one should take a stress approach and be self-consistent, and then you jumped over to currents, and then when you went to currents, you drew currents only more or less at ionospheric levels, and to complete continuity across the low latitude part of your convection diagram there. How do you complete that continuity? On the closed field line portion, I know one can draw very fancy diagrams relative to closing way out someplace, but you were drawing a current essentially crossing the auroral belt convection. What do you do with the low latitude edge of that current?
I haven't quite got you straight, Jim.
I'm trying to find out where that current closes.
Outside or
Yes, and what the mechanism is out in the magnetosphere that closes the current.
Well,
Cross field lines.
the diagrams that I gave earlier were intended to show that there are, in fact, many reasons for currents going perpendicular to field lines in the outer magnetosphere. Notably, all the terms in that equation, gradient of pressure, for example, always makes a perpendicular current. The inertia of the plasma, if that matters, always makes a perpendicular current. The stresses exerted by the solar wind are the most important thing, I suppose. They make currents which go across field lines, as I tried to indicate. But it is, in fact, an extremely difficult problem. You can't, just thinking of the currents themselves, decide where they flow. It's just not reasonable even to start that. You have to know what the stress balance is first, and you work the entire problem out self-consistently, and then you'll know where the currents flow.
Basically, my question is to whether you aren't better off sticking to stresses.
Of course. I mean, that's
And if you don't really run into having to do a lot of very, that's definitely hand waving when you come to closing in the inner magnetosphere portions, particularly.
well, I'm glad you said that, because I mean that's really my attitude to this all along.
And which also, when it comes to your limiting current, I would get the feeling that you're more likely to run into that limitation out in the magnetosphere than you are in the ionosphere.
It's not so clear to me, but I certainly agree. It's a waste of time trying to understand the magnetosphere starting with the currents. In fact, it's not only a waste of time, you can't do it. You have to do it the way you said, self-consistently using stresses, and then B rather than J first. But then it's important to look at the electric field, the electric fields and the currents that you've generated as a result of this to see if they're reasonable. Because in your treatment you will have had to make a number of approximations which may not be valid. And that's why I said that such a treatment will inevitably lead to infinities in the current density. And you have to decide how reasonable that is, and whether a simple, reasonable processes which will just remove the infinity without changing what you thought you had.
Then would this go back to saying that the limitation is the generator itself?
I think no. If you do something, if you don't allow the current to flow the way you thought it ought to, I think you have to start all over again. And I don't know how you do that either. Magnetosphere is a much more complicated place than we usually take it for.
Ian, can you say again how the change in the stress balance in your development of ideas took a neutral point and developed it into a neutral line?
It's big hand wave. I'll explain what it means. It's inevitable in a Chapman-Ferraro type thing that it's just a neutral point. Of course, if you allow the plasma to sort of go down the hole, then it spreads out.
You want to get a neutral point there because of symmetry and other conditions as well. But I just thought you might be able to say more on that. But do you feel in some way that neutral line is favored by, particle data in the cusp?
You mean in the cusp?
Yeah.
Well, I'm always biased about everything, and I think that there's no doubt that the cusp is associated with field line reconnection on the day side or all the way around the magnetosphere, and that it's a line. It's
so there'd be a
connected
line.
to a neutral line, yeah.
Just as a comment on that neutral point, neutral line business, for reconnection there only needs to be just a neutral point, but there could be a very thin current sheet with a very weak normal field distributed around the magnetosphere, which would give the appearance of a neutral line. But like the Cowley, his topological model that he presented last summer, there's sort of a diffusion surface, which might be sort of the mapping of the cusp surface around the magnetosphere, and so that magnetic field lines from the solar wind that impinge on this surface sort of get swept into the neutral point from wherever they graze the magnetosphere, so that the reconnection would only take place really at a point. Just sort of at least it seems a matter of distinction between that kind of a diffusion surface and a real neutral line.
Yeah, I don't really understand what Cowley did. It looked very reasonable, but I still didn't understand it. But it doesn't make sense to me that you only have a neutral point reconnection on the front surface, because then, if you think of it, you can only have one field line at a time from the solar wind coming in and reconnecting, which is very inconvenient. You can't carry much pointing flux that way. And it's much better to have a whole line gobble up the field.
I think that was sort of the point of Cowley's picture, though, was that even though the actual reconnection only took place at a point, that all the field lines that come in and impinge on this diffusion surface get swept. There's no longer frozen field in the diffusion surface, and so the magnetic field lines get distorted quite rapidly until their end gets brought into the across the neutral point. So in that picture, at least it's possible that you can have essentially merging of field lines over a wide part of the magnetopause, all field lines that hit this diffusion surface in essence. But the actual reconnection, there need only be a neutral point, not a neutral line. Maybe there is a neutral line, in which case it works too, but it's not necessary, I don't think.
By the way, the discussion that brought this up there was referred to a line of field lines at ionospheric levels which go out, rather than a single line, a single field line, as in the Chapman Ferrari model. So we may be getting at some confusion as a result of this discussion, I think. Apart from the fact that I still don't understand what Cowley did, but your explanation was very good.
I think we have a problem with nomenclature, whereas the neutral line isn't neutral, just like the neutral sheet isn't neutral, and that the merging line can have fields parallel to it. I think Stern has pointed this out fairly clearly in his attempt to show what the magnetosphere looks like from a theoretical point of view. That the field can lie parallel to the neutral sheet, and therefore an experimentalist wouldn't see it as being neutral or a neutral line. But there certainly would be merging all along it.
Yeah, I don't like to get into these long discussions about the topology of field lines around neutral points and lines. It seems to be a can of worms, to say the least. But I agree that there's awful problems about nomenclature. The only thing that's been properly named so far is the magnetosphere, which everyone seems to forget. All the other words...
But it's not a sphere.
But all the other words that we use so freely, as you indicated, neutral points, neutral lines, and so on, are all very bad, including, by the way, the word convection, which I really know how it arose, because I was sitting there when it happened, and nobody thought a thing about what it meant at all. They simply started to use the word, and without thinking why it should mean anything in particular. And it's stuck with us like anything ever since. I think I know what it means, but it doesn't mean that to most people, and it doesn't mean much anymore. But we all know what we want it to mean, which is the main thing about nomenclature.